All right. Well, thanks for having me, everyone. I've got a lot of slides to show, but Shawn asked to kind of highlight some findings in the field, so I'm going to try to highlight some of that and go through a lot of stuff. Just backing up, big picture, Ecotope works on we work on energy efficiency, but mostly focused on research and design. Most of California knows our research side, mostly around heat pump water heating. I want to show you some of the other sides that we work on, but mostly existing buildings is a big piece. We developed the decarbonization plan for the entire city of Seattle in the last 10 years. So now we are implementing. Clean buildings is a new policy that's coming along, across the U.S. So we're moving a lot in that space. But without further ado, let's get started. So big picture, I wanted to kind of talk about kind of the energy demands growing. We haven't talked much about that, but from a nation, so we'll kind of see what's happening, and I'll give you a perspective from the Pacific Northwest. I want to talk about some lessons learned with central heat pump water heating. We've been working on this since 2009. We've designed 100 plus systems. We've got a new data collection system that is super powerful. We can do just about anything with these heat pump water heating systems now. So I'll show you some of that. I want to show you, this is sort of an adage to Amory Levin's tunneling through the cost barrier. I've done this on 4 projects. I want to show you one with a passive house, multifamily. Some pretty amazing things happen when you push it. And then I want to talk to you about another kind of emerging trend around IAQ in buildings. Wildfire smoke in particular, PM 2.5. It's a real threat in our buildings, and so we've designed a system in Portland that sort of mitigates it. So I'm going to show you that. So carry on. Okay, so I'm going to go kind of fast. So the energy demand growth. This was McKinsey report, but it's basically showing from now till 2040 steady growth. And the areas that we're seeing growth is hydrogen production, transport, data center, industrial, connective. So that's all kind of big picture data projection, but there's essentially a lot of growth happening now, about 3.5% per year from now till 2040. The same thing is happening next. Oh, sorry. I think that's just electrification. Oh, okay. So a lot of the electrification for industrial and buildings, that's sort of the impact there. I don't know a lot about that. I just kind of pulled it up. But next slide. But just kind of reiterating, this is the Pacific Northwest grids. So this would be Washington, Oregon, Montana, Idaho. We are a winter peaking utility, closely becoming a summer peaking utility. And there's our annual kind of average megawatt hour. But the gist is the grid's about 50% occupied, and because of peaking, we need another 50% to handle that one day. So that's the real crux of the problem here is we've got a grid that's this big, and we've got capacity at this big, but every once in a while we get these spikes. So those spikes are valuable energy. Next. This is what they're projecting in the 9th Power Plan. So every 4 or 5 years in the Pacific Northwest, they kind of reorient the power planning. But there's this huge tech load forecast. So this is the AI data server. And this is like just coming on way faster than anything else. Transportation and then hydrogen. So there's this creation of a hydrogen economy. I don't know anything about that, but that's just what's being shown. So, yeah. Okay, next. So then Pacific Northwest is about 60% hydro baseload, so much different energy than anything we have in California. And then we have another 25% of it is alternate kind of modern renewables, and then there's fossil. But this is where the growth's going to come from in the next 10 to 15 years in the Northwest. But it's mostly clean. But this peaking thing, there's 2 pieces there. One is natural gas turbines. We've never had to engage natural gas turbines in the Northwest. We've met all of future load growth with conservation. So we are now out of that mode right now because the growth is so high. So they're putting 80 gas turbines in the Pacific Northwest for peaking.
How many?
80. So that's what's happening, and that's the reality. The other place that we're going to find this energy is load shift. So that one day moving stuff around, right? So that's painting the picture of what's kind of happening. Next. So now I want to jump into some stuff. So Like I said, so Ecotope is focused on sort of trying or finding responses to a lot of these issues. So the utilities come and say, we have peaking problems, we have other stuff. And so we've been focused on load shifting, heat pump water heating. That's kind of the promise. And so I want to show you two projects that we've done this on just to kind of paint it. Right now we've got about 50 heat pump water heating sites that we're monitoring. This is 1 minute data. It's super valuable stuff. We developed a new tool called Ecotope. It can do M&V on hot water systems. It's a dashboard, it's a diagnostic tool, and it also can automate load shift. And so we've done a lot of automation on that to try to work around. Go ahead.
What are the size of the heat pumps in this?
Oh, in this one, this is a Mitsubishi 10-ton or 11-ton heat pump, and I'll show. Yeah, they're kind of bigger central. Okay. Next. So this is a project we did. This is one of the first Mitsubishi heat pump water heaters where it was built in a factory. So it's this idea of trying to scale. Go to next. And so this was an existing building, 100 units. It was heated with electric. Remember, Seattle electricity rates 20 years ago were 3 cents a kilowatt hour, flat, right? So everything built in the 70s and 80s, I mean, it's cheap hydro, right? Hydro costs half a penny a kilowatt hour. That's all in. So it's super cheap power, but the problem is it's all used up, right? And so now we're in the growth era. So this was a project. We got some funding to do this. Go next. Those are kind of the background prices. This is an electric plant. We've seen this plenty of times. This was built on a skid in a factory and shipped out. Go next. You can kind of see it in play. That's the skid over to the right. And then this is us arriving. It took 4 hours to connect it up. It was pretty quick. You have to do some revalving inside to kind of get ready for it. So you have some redundancy, and then you plug this thing in and switch it over. So we've done that now on about 10 projects, pretty straightforward. There's some steps you have to follow. Next. And then here's kind of this is kind of the results. So green was the existing electric. When we put the heat pump technology in, that was the blue, and the red, and this is the power used, energy, and the red shows when we've load shift. So we can load shift now the morning and the evening. This was sized for load shift. So it sort of shows, we can do this now. Next. And here's the savings. So this was the baseline was 70 kilowatt hours from 6 to 9 and 6 to 9. So those are kind of the two peaks. But we can see that, massive reduction just with the heat pump technology alone. You're 2/3 there, and then when you shift out a peak, you're there. So there's 70 kilowatt hours in 3 hours that was sort of shifted, and so we can do that. Seattle City Lights, very happy about this. They've asked us for more, so we're working a little bit bigger. Getting 10 buildings and doing all those together. So kind of seeing what the impact is. So next. This is another one I did. So same project, research team did this. I didn't personally do this. I helped with design. Next. So this was PG&E territory. And this was 2 buildings. Both were replaced with Mitsubishi QAHVs. Next. So they were gas replaced with Mitsubishis. They're about the same number of units, 120, 130, so good case. One of the buildings has a much higher recirc load than the other. Next. This just shows the data. This is pretty interesting. This shows kind of, our standard 16 GPM for 140 units. That's our peak. 16 GPM for 140 units. So this sort of validates some of Appendix M's findings, and then you get an occasional 0.1. We found it's about between 0.15, 0.2 GPM per occupant is your peak. So that, and Appendix M will arrive about half, or about double what you actually see. So you're safe using Appendix M, the water WDC calculator, if you're familiar with sizing. Anyway, let's go next on that. So this is just more data. So this was an experiment. We did 7 different load shift schedules. So we tried a bunch of different stuff. And so what we were chasing were just energy reduction, greenhouse gas emissions, and then total total benefit, total system benefit. So we ran through all these different scenarios using our EcoDash programming to try to see, here's normal operation. We have a load up. We have, this scenario. I can't remember what these are. This is we cut the swing tank off. So we tried a bunch of different scenarios. There's a CalNex report. That's who funded this, and you can read all the details in it if you just Google it. I'm happy to send it to you if you come up, send me an email. But anyway, next slide. So this is an example of like Schedule 7. So we show, heat pump water heater 1 and 2. We show a ramp up, a load up, and a shed. That just kind of shows an example of what's happening. So this is a way to shift out of that peak. And if everyone sort of does it, then the theory is we'll see more capacity freed up. And that's kind of that's what we're chasing with this particular technology. Next. But the takeaway was we couldn't find one control strategy that would deliver all of the benefits, right? You could do this one and you get good, energy cost reduction, but it comes at a cost of something else. So we can't really arrive at this ideal state where you get everything. We can't do it right now, or maybe somebody else will figure this out. But this was what we found. So that's the takeaway of this is that you can't get all of them right now with how we tried it.
Greg, would you confirm or deny with our load shift work what he's saying?
He's saying that you can't simultaneously hit all of it.
Yeah.
I mean, it depends. Devil's in the details, right? It depends. Like, what's your local grid look like? What are what your occupants' preferences? But yeah, there's lots of simultaneously not always overlapping things that you're trying to.
Yeah.
So yeah, same experience.
I have a lot to get through. Go ahead, quick.
Just quickly, I would say, like, working on these two projects, they have some of the worst distribution systems that you ever see in multifamily buildings. So
Yes.
if you can do it here, you should be able to do it everywhere.
Yes. And you can turn off your swing tank in peak. There's enough draw out of the main, so you can just turn that off, and that can be super helpful. So we did that here. But that was sort of the finding. This is PG&E's grid.
And these reductions are compared to what?
To the gas baseline.
How can there be only an 8% greenhouse gas reduction in gas baseline? Shouldn't the greenhouse gas reduction
I'm sorry, that's just with the load shift. I'm sorry, there's another slide that covers what you're after.
Oh.
This is just, okay, we've done the heat
compared
pump.
to unload
Now
shifting
we've got,
electric?
what can we get with load
Okay.
shift and
Yeah.
satisfy all of this? That's kind of the crux.
Got it, thanks.
So if it was just load shift, then how did you see cost, like energy savings, energy reduction in the first line?
So you're focused really on there's no swing tank operation, one heat pump, not two, and you're just pulsing along,
Oh, I see.
right? And so that's one run. And then we do another one where we load up earlier with two heat pumps,
Exactly.
powerhouse, and then coast through. So it's just kind of testing the sensitivity of that.
But if it is the regular operation with two heat pumps
Yeah.
and preheating, then you wouldn't expect any energy savings. Right? It's just shifting the load to different hours.
Yeah. I mean, and there's different scenarios in there. It's hard to kind of summarize, but the report does a pretty good job at kind of showing the results. I'd encourage you to read that. But I mean, that's kind of the simple takeaway. Next. And so this is kind of the summary results. And so we monitored these for about, a half a year or so. Tons of savings, 68%. So there's your greenhouse gas emission just with that. 90% reduction on both of the sites. But this is the kind of the crux takeaway is that we reduced the energy use, we did the best we could with load shift, and we doubled the cost compared to the baseline. So the tenants are paying twice as much for gas with a very, 2.7 COP heat pump. We're doing load shift, we're doing everything, and there's still cost 2x. That is a problem. So
That's gas compared to the electric.
gas compared to this high efficiency 2.7 COP with load shift, we stay out of the peaks, and we're still 2x. And it's because of the demand charges. So we need demand charge reform. That's really what it comes down to.
You can punt on this question for time, but
Yeah.
I want to understand how you did these comparisons because with a, even if you have a large system, comparing apples to apples, when demand patterns change and even the grid changes, right? Like comparing counterfactuals for like what the grid looks like today versus 2 weeks ago.
Totally.
There's like lots of things that are really dynamic. So I just wanted to understand that.
Yeah, that's a great point. I mean, I think this one was just pretty, just straight PG&E kind of grid and the rates. Andy?
Yeah, what fraction of the energy use in a typical water heater system is swing tank roughly? Because if they have really bad distribution issues, I'm wondering if it's like an overwhelming amount of electric resistance that's really dragging us down, or if this is more representative?
That's a really good question. I didn't do this research. I'm kind of just more reporting on it. Scott would be the person to ask, but this was the bigger research load. So we, for whatever reason, but I think it really came down to one of the swing tanks was a lot higher wattage than the other one, and so just by nature of that, like that happens. Just as an aside, we've been optimizing swing tank, and we've got a job in Portland where we had 15% of the energy with swing tank just by optimizing the control of that swing tank, i.e. we use an electric boiler, forget the elements, because you can't control them, they're black box. But just by optimizing that, we took it from 15% of the load to 2. And what you do is you say, whoa, back off. Because there's a sensor at the bottom of the tank that starts the resistance going, like, as soon as it's 2 degrees up. Like, let's go, hurry, we gotta get. And it's like, if you can get control of that, which you can't with a tank type, but if you can, then you can push it off by saying, whoa, let's hold off, and then put it on. So, a lot of focus there, but optimizing the control of that backup is super important. Next, sorry, go ahead, Tanya.
I just wondered whether or not you've integrated this, and I know we have been talking to Ecotope about this with HVAC controls. I mean, part of the issue is we need demand charges because there are capacity issues at feeders, there are capacity issues in the distribution grid, the wholesale market as well.
Right.
And so if you just make that time-based demand charges, well, now you're just going to shift the peak to elsewhere. So great, you shifted load earlier in the morning, but now we see everybody's EVs or water heaters starting earlier, so you just shift it and actually mitigate.
Right.
So demand charges are supposed to send a signal. I think you're right. They're not necessarily sending the right signal. But as somebody who's been on the sort of prices to devices train for many years, the problem is that technologies are not able to, you could fix that with the real-time pricing programs like PG&E and SE are experimenting with, by just having one price.
Yeah.
All of it's in there. Energy, distribution, flat charges, etc. And you can change it every day. It's a 24-hour ahead hourly price. The problem is, can your controls respond to that signal?
Right.
And I think, so that's the thing that worries me a little bit when we're like, let's get rid of demand charge. I'm like, well, that defeats the point. But then trying to make it time dependent, we'll just do what happened with TOU. Now you've got to shift the TOU to a different hour because you just keep pushing the problem to different times of day as opposed to communicating what the supply-demand imbalance is through a price that incorporates all of it. It would actually be easy for a machine to understand, but would be very difficult for a human operator.
Yeah, that's a really good point. Yeah, I mean, this is, I think, just kind of the surface. Oh, I'm sorry. Yeah.
Good, I didn't mean to interrupt.
Yep.
Well, the question I have a lot of times when people look at the cost of gas versus electric is that we also hear that over time there's an expectation at some point the price of gas is going to cross over because of the reduced number of users. Does anybody ever look at sort of the life cycle cost or cost for the next 20 years as opposed to the cost today in terms of the billing impact?
That's a really good, I mean, I know I've seen some models NREL's been developing, so I think at that point, but and I've seen a lot of projections about the future, the burden and the burden kind of cost of gas, but it hasn't showed up really yet, so yeah, but I guess I don't know a lot about that, but
Yeah, it seems like that should be part of the narrative.
Right.
Today, it's more, but over time, we expect at some point it'll cross over and actually be cheaper.
yeah.
Wouldn't it happen with exporters LNG that even if demand is going down in the U.S., what they'll do is increase the exports.
gas will go up.
Let's keep Shawn going.
Gas is being covered.
Before we're making this side conversation, keep on going, man.
Next. Okay, anyway, just making that point, the demand charges are really showing up here, and unfortunately, so we've done a good job. Yeah, they kind of wash out all your load shift and COP savings. So next, go ahead.
Oh, why is the COP so low?
No, that's what we get here. Yeah, you don't get more than that. You get manufacturers' claims 4.5 and 6. That's one data point. But the COPs here include recirc. They include the recirc losses. So it's a total system COP, not the heat pump. The heat pump's usually maybe a half a COP more, but then you got to factor in. But that's kind of how NEA has been establishing performance is total system COP. So another one I want to go back one. So this is an area that we've been exploring now, and it's for doing space heating. So flexible load buildings are an area that we're focused on. It's the ability to use hot water and space heat energy kind of when you want to. And so, obviously we use storage, thermal storage to make that happen. Next. I don't know has anyone heard of tunneling through the cost barrier? Okay, so I've been really interested in this. I've done this now on 4 projects. It's pretty amazing what happens, but you push past your kind of standard cost effectiveness limit, and as you keep adding efficiency, this red line, it keeps going up. You get to a point where you've reduced the load so much that you see the benefit, but you can also mess this up. So Amory Lovin says, integrated design is kind of how you pull this off. And so you have to do all the right things to actually see the magic. And the magic is all in on the envelope and air tightness and heat recovery ventilation, and the load is tiny, right? So you've kind of shift the funding from mechanical budget to envelope and load reduction. That's the tunneling magic. I've done that on 4 projects, all different end use, and the same thing happens. So it works. Next. This is a project we're doing in Seattle. It is low-income senior housing, 100 units. This project has flexible load hot water, flexible load space heat. The space heat is hydronic based with 3 air source heat pumps on the roof feeding a big hydronic loop. Next. The hot water is also load shift. So we've developed a new product called Ecotope pipe. This is a seasonal changeover load shiftable hot water or space heating system. And so it's 2 pipes, big storage in the basement, heat pumps on the roof. So instead of having 90 heat pumps to take care of, we have 3. They're 18 tons each, a lot smaller. The maintenance costs in senior housing is a big number, especially with heat pumps. Most of the staff don't understand heat pumps. They just throw their hands up. And so what they're asking us is we want, central systems where we can just work on a couple. And so we're seeing that because these, the through walls that break after 3 years and these things, it's starting to wear them down. The other side is just the passive house. So this is an effort at trying to kind of combine them both, and really it's a response to kind of resiliency. So if we have disruption in the future, the idea is you've got this really highly efficient envelope. You can kind of coast a few days. You've got thermal storage. This building also has a diesel genset that'll it can go for 5 days. So that was actually part of the HUD requirement. Next. So this is kind of breaking this down, but kind of the reveal here is for 90 units, we ended up with 23-ton load. That's, typical load is like a ton a unit. But if you size an apartment on the block load and not the individual load, so the block load would be the whole building load, and size your plant to that, then you kind of follow the sun around the load. So the morning you kind of taking care of the east side, the evening you're taking care of the west side, but you don't need the coincident load, you just need the block load, the peak for the whole building. So when you do that, now you're buying, a bunch less heat pumps. So you're, about $500,000 in saved HVAC costs that goes towards the passive house.
I just know that you can't buy heat pumps that small, so this approach is important because the smallest heat pump you get for a house is 8,000 BTUs, and you're using less than that even.
Well, that's 23 tons, which is 12,000.
5 tons per apartment.
Yeah.
That's what it means, like,
Right.
apartment one's even that small.
Right.
So
Good point. Yeah. So the idea here is just you got one set and you got some big storage, and so you kind of take care of and chase the block load in the building. Next.
And this is So like heating, cooling both?
It is,
So
heating and
it's like
cooling.
heat recovery?
No, it's just two-pipe hydronic.
Okay.
So you have a heating season and you have a cooling season. That's it. It's kind of standard. It's passive house, so we've said you get a little electric heater or open a window in those swing seasons if we're not ready for cooling. So it's sort of like pushing this burden a little bit onto the kind of the owners and saying, you know, your part here is, you know, we're going to do our part. You got two pipes, you get heat or cool. We'll provide you there, but in the middle, you know, you guys can kind of monitor your temperature with backup or. But,
I'm not
yeah.
an expert, but what do you consider as the common use areas heat or cooling? Like how much percentage is on for the
Yeah, so there's.
apartment?
Yeah, that's a good. It's probably in this place. There's 90% common, or sorry, 90% apartment and 10% common area.
Okay,
Just-
so you add up to that the total?
The commercial space on the ground floor, which is the common area amenity, that's actually just a split heat pump.
Okay.
So we didn't put that on the system because in meeting rooms, sometimes in the winter you need cooling, and so just don't fight it. Just add that. So that's what we did there. Next. Oh, the other thing I was going to mention is it's got 5 days of backup power. So this came out of the HUD loan for this project. And the owner said, we need 5 days of outage coverage. So that is what is showing up today in our HUD loan requirement for this project. So we've got a big diesel gen set. And then we've got an emergency circuit in there, and there's a second phase going in, and we're going to try to put a battery in, and then we can use the diesel for the battery, the solar, and so we'll try to keep building on that concept. But just kind of continuing to push on this flexible load building. And then we're going to start in on experiments next year once it's built, but it's just getting built now. So next. And this is the kind of the last piece. I mentioned the wildfire smoke. We get a lot more requests for filtering wildfire smoke getting into the buildings. Thanks. So I'll show you a renovation of an office building in downtown Portland. So this is an old historic building, single pane windows. It was built, you know, turn of the century, or yeah, I guess 1920. Yeah, turn of the century, last century. And it's got an EUI of 25. And we.
That's what I said.
So what we did here, I'll show you some more next. And so this building was built around a concept that we've come up with called design for off. And so the idea is you run the building in active mode, you run it in passive mode, and you run it in IAQ mode. And so we have sensors.
Indoor air quality.
Indoor air quality mode. So we can look at the outside PM 2.5, which is particulate matter 2.5 or less. That's the stuff that stays in. And we can trigger this system on. So I'll show you. So the way that it works, go back real quick. We've got a regular ERV system, so energy recovery ventilation system. What we do is on the supply side, we add a supply fan and a HEPA filter and a carbon filter. And the idea is that we pressurize this space. So now nothing can infiltrate in, right? That's one source of wildfire smoke. And then you're forcing all of this filtered air in. So you get a double effect. You're pressurizing, pushing anything from coming in, and everything that is going in is getting filtered with HEPA 18. HEPA filters, MERV 18, and carbon for the smell. But in Portland, they get a lot of wildfire smoke in downtown. Also, the urban core is super polluted. Go next. So this is just showing the design and plan. This is the ERV. What we ended up doing, this is over to the right, is a section. And so you use the vertical space, go down, over, and back up. So it's just a little bypass. Put some dampers in. We're still using the base exhaust, but we can control both the supply and exhaust. And so we set the building pressure up about 03, so not very much.
Is it manual or is it actually?
It's automated.
So it's sensing PM or something?
Yeah. Yeah, I'll show you this the graph. Thanks. Next. Sorry. We're getting close. So this shows it in action. So the ERV's up here, kind of comes down, shows a fan, and there's our filter rack. Shows the HEPA filter. So next. This is another one. It's on the roof. You kind of, yeah, we've designed it and they've built it.
That's cool.
Yeah. So then next. So this shows kind of what's happening indoors. This is the blue is the operation of the ERV in one zone, and we can see the PM 2.5 levels. So they come up, then the ERV turns on and pushes them down. They come up, we push them down. That's what we do in buildings all day, right? It's a sensor, we push that down. And so you can kind of see, you look down at the bottom, you can see we've got these kind of custom lights that were designed, and they sit in front of all the windows. And so the occupants know when it turns green, they open the windows. When it's not, when it's red, you close them. And then when it's in IAQ mode, you close them. And that turns red or orange, the IAQ mode. Next, and this is the last piece. So this is a sample of April in Portland. The outdoor urban PM 2.5 level is showing the light gray, and the darker blue is showing the indoor level. So you can see we've kind of mitigated the impact.
What's the dotted line?
The dotted line is the threshold by EPA for PM 2.5 indoors. And this is a mild month. When the fires came, this line was up here, and we were still down here. And I couldn't find that graph, but it happens in August, so it's happening now probably, because we got tons of fire. So
you're switching modes. You can't do cooling while you're in this.
no, you can.
Because why are you turning it on and off all the time?
So in the Northwest, 50% of the year we don't need HVAC, and it happens 2 months on the spring and 2 months on the side. Same thing as here, but there's nothing more efficient than off, right? That's the idea. So we're trying to, when we need heat, we use it. Then we turn it off in the swing, and then IAQ in the summer. It can be heat or cool. But the idea is that we're pressurizing the space.
But you can do it simultaneously.
We can. Yep. And I think that's the end. Thank you.